Hello, well, everybody. I'm going to talk about how we obtained numerical solutions to a bi-level parameter optimization problem in the context of image denoising. This is part of a joint work with Juan Carlos de los Reyes and Marta. And well, since so far I'm the only talk discussing images, let me give you some insights. So basically, when we want to capture an image that is usually clean, has distinct features, and we use a camera, this camera will add some artifacts to the digital image. That will be usually modeled as some additive Gaussian noise. And this is quite troublesome for some image related tasks like classification, feature detection, etc. So it's quite crucial to get some sort of clean image digitally as well. There are several methods to do this. And well, as you may have guessed, there are non-local methods to do it as well. These are associated mainly by the kernel that is used to perform the regularization. And they have practically very good results in the sense that they usually conserve textures, edges, and even the contrast of the image that, well, local methods usually fail at that. And they also require very little regularity in terms of the functional spaces where everything is posed. Okay, so the most famous kernel currently known is the non-local means kernel. And in this setting, we will discuss it a little bit more. So basically, a non-local means kernel is a dissimilarity measure between patches of the image, patches of pixels that are weighted by some weight named W. If we get this kernel into a semi-norm structure, we can obtain a regularized image by solving a variational problem of this form, where here lambda is going to be a kernel regularizer or a data fidelity term. Okay, so now you can guess that if you pick different W's and different lambdas, you will get different quality measures of the reconstructions, which is displayed in this picture here, and is actually quite a cumbersome place to optimize. But in any case, well, we would like to know for a noisy image, which is the best pair of parameters that would get the best reconstruction, right? So we did this in separate ways. We optimize from one side just the fidelity weight, on the other side just the kernel weight. Both are proposed as bi-level optimization problems or optimal control problems in functional spaces, where we want to optimize some loss function. Given a clean image, we want to minimize this difference that will give us the best parameters for fitting the model that we have. Okay, so we followed an optimized and discretized approach, and that gave us some analytical results. In terms of the fidelity term, we optimized it on a functional space with at least one derivative that is constrained on that is bounded. And in case of the kernel, that was done on a finite dimensional space inside square integrable functions that are also bounded. But since it's finite dimensional, we can actually consider this just as a interval, closed interval. Both adjoint and the state equations are shared between the two models, but the derivatives of the reduced objectives are quite different. In the sense of, in the case of the fidelity weight, we have to solve a PDE, while in the case of the kernel weight, we only have to apply some sort of non-local dot product, where the kernel is basically based on the original kernel that we had before. Okay, so now we want solutions. We implemented everything on Python. Since the adjoint and the state equations are posed just on L2, this means that we can use just piecewise constant elements for both the kernel and solve those equations. But in the case of the elliptic partial differential equation that we have to somehow get some more regularity that fits the same mesh that the piecewise constant elements had. So in that case, we use the piecewise bilinear elements with Phoenix. In the end, we grab up a bunch of different notebooks, Jupyter notebooks, showcasing different, well, all the capabilities that we could figure out with our code and with the theory that we had developed. That includes the case of optimizing the scalar parameter, well, lambda as a scalar parameter, as a spatial parameter, with the finite element discretization, but also in an additional finite difference discretization, which has a little bit of benefit in the case that the number of unknowns is a little bit reduced, not so much, but a little bit. And also the optimization of the scalar weight. We also have a model for training the scalar parameter lambda in cases, well, we want a data set of images that are clean, and we have another that is noisy, and we want to find the best parameter lambda. Okay, so the crucial thing here is how to compute the kernel. And well, in the basis that I have mentioned so far, the piecewise constant elements, this continuous expression that we have here reduces just to basic pointwise evaluation of the functions involved. In this case, f is the noisy image. But if we do it naively, well, we all know that it's quite well, it will require a lot of computational power and memory. Usually this would take, well, for a small image of 256 squared pixels, that would take around 48 hours just to compute the matrix. So we have to get another way to do it. So an alternative path to do this is, well, considering some additional, well, expansions of this exponential term. So if we figure out how to store some of the elements in memory beforehand, we will be able to do it very fast. So basically, if we pre-compute the patches of the pixels around, of each pixel, and compute their measure, that is just the sum of their intensities, we will, well, basically be done. We can also adjust interaction radius such that not every pixel is a neighbor with each other, just some bands of pixels. We will store just entries that have low similarity, since, well, we have this interpretation of the kernel as a dissimilarity measure. And, well, high dissimilarity values would not contribute at all to the reconstruction. And also, well, we have a symmetric kernel, so only the lower triangle is needed to really be stored. In any case, we reduce the complexity measure that we had before to this expression that we have here. And in terms of speed, well, it reduces the computation to around 20 seconds. From 40 hours to 20 seconds is quite a difference, right? Now, we want to solve the optimal control problem, right? So now the problem is that optimal control setting is non-convex, it's differentiable, but it also has box constraints. So to optimize there, we use a trust region type algorithm aided by a limited memory procedure, which is updated with the derivative of the reduced objective function using the joint equations. For the state and the joint equations, we use a Krylov method. And I have to mention here also that the update on the kernel, if we want to change the weight, this is just, well, by the definition of the kernel, it's just a component-wise power. So we don't need to recompute the kernel over and over again when we just want to update W. Okay. In the repository, you will find several experiments for all the different cases that I have discussed so far. And you will be able to see as well that, well, the best reconstruction that we can obtain is when we we overfit with a differentiable function. However, the scalar values for optimizing just lambda or w end up with a very good reconstruction that is quite competitive with respect to the spatial one. And yeah, this will be just comparing models. But finally, if we compare this to the standard local perspectives, we see, well, what we wanted, right? We wanted a model that in the end will result in the conservation of edges, in the conservation of contrast, and that wouldn't showcase some of the downsides of local methods like the staircase effect. Okay, so that's pretty much everything that I wanted to say. And well, yeah, there are some extensions that we might be interested in working in the future, but that's all for now.